All right. Okay. So yesterday it was all about indefinite integrals, right? That's where those integrals where we have no limits of integration, and when we end up with our final answer, we have that plus c tacked on to the end, right? Because we're at the antiderivative. We want to come up with a general antiderivative solution. All right. Today we're going to be looking at definite integrals and how we use U substitution in those scenarios. Okay. When it comes to definite integrals, you can still integrate and use the fundamental theorem of calculus to evaluate the bounds. Okay. Another method is to rewrite the definite integral limits when you do the U substitution. Okay. So I'll show you kind of like both of these ways. So essentially, there's kind of like two different strategies to take. This kind of situation, I think there is one that I would kind of recommend that you utilize, but really either one will work. But it seems that the AP test kind of like favors asking questions about one of the particular strategies, or in regards to one of the particular strategies. So whichever one you want to use, it's fine, but just you should be familiar with both and be able to like recognize and use both if necessary. Okay, so that being said, right, we look at something like letter A here. We want to integrate from 1 to 5 dx over the square root of 10x minus 1, okay, that quantity. So first of all, before I do this, understand, right, that this is the same thing as asking the integral from 1 to 5 of 1 over the square root of 10x minus 1, and like the dx is outside here, right? That dx is being multiplied with this quantity, and so, it's like you can think of it as like dx over 1, the dx would go up in the numerator, the 1 would be down in the denominator, and that's how you end up with this, okay? So don't, get weirded out by the fact that the dx is up there. Sometimes it's written up there, especially when you have fractions with just a numerator of 1. Typical way of doing things here, right? Okay. So again, clearly this is a U substitution, right? We're in that section. So what should we let our U be here? 10x minus 1. Okay, exactly right. That is something that is inside the square root function there. So we'll try and let your U be 10x minus 1. And so then du equals just 10 dx. Okay. Again, I'm skipping that step where I write, du dx equals 10, and then multiplying the dx over. I'm just kind of getting right down to the nitty-gritty there. Okay, just du equals 10 dx. All right, feel free to keep writing that intermediate step if you want, right? So, okay, let's see here. Do we have 10 dx in our integrand here? No, so we need to rewrite further here, or divide that 10 over, make it 1/10 du equals dx. And now we can substitute in for the dx right there. And so now I'm going to write the integral, and it'll be, and if you'll permit me here, I'm going to go ahead and just write that as u to the negative 1/2 du. Thank you, sorry, a 1/10 in front, yes. Okay. Notice what I did not write, though, and this one, the 1/10 was not on purpose. That was just me, making a mistake there. But what did I leave out? The limits of integration, right? Why did I leave out these limits of integration? Well, 1 and 5 were the limits of integration for what variable? X. We're now in terms of u. So it would be, highly unlikely that this 1 and 5, which are the limits of integration for x, would be the same exact limits of integration for u. In fact, it's almost guaranteed that they won't be the same. Okay. So what we're going to do now is proceed as if this were an indefinite integral. This is option 1. Okay. So this point is where we kind of like branch off. Option 1 is we proceed right now as if this thing is an indefinite integral. Integrate like we did yesterday, and then we'll resubstitute back in for the 10x minus 1 for our u's. Then we'll evaluate from 1 to 5. Okay, so we're gonna use the U substitution to allow us to integrate retranslate it, right? Translate it back into terms of x, and then use the 1 and the 5, which are our x limits of integration. So that's option 1. Okay, so this is like kind of option 1 here. Okay, and so integral of u to the negative 1/2, we'll add 1 to our u. Oops, I'm getting ahead of myself here. So u to the 1/2 over 1/2, right? At this point, we should probably put a plus c in because we are kind of doing an indefinite integral. So it's probably, mathematically a good idea to do that. And so we'll end up with 1/5, right? Dividing by 1/2 is the same thing as multiplying by 2. 2 times 1/10 gives us the 1/5 there. U to the 1/2 plus c. And so it's 1/5 times 10x minus 1 to the 1/2 plus c. And now we will evaluate that finally now from 1 to 5. Okay. So we re-substitute it in for the x. And now we can use that 1 and 5. We'll evaluate from 1 to 5 there. Okay. And so we'll have 1/5 times 10 times 5 minus 1 to the 1/2 minus 1/5 times 10 times 1 minus 1 to the 1/2. Bless you. Okay, and again, the c's cancel out, so we don't need to write them at that point. Okay. Excuse me. At this point, we're done, right? We could stop. But, 10 times 5 is 50, minus 1 is 49. 49 to the 1/2 is 7, so we get 7/5. Minus 10 times 1 is 10, minus 1 is 9. 9 to the 1/2 is 3, 3/5. Okay, and so we get 4/5 there. Okay. But, of course, you could have stopped right here if it was multiple choice or something like that. Or, sorry, if it was a free response question. Okay, if it was multiple choice, you may need to be able to simplify it down to 4/5 there. So I would recommend you give yourself that practice, okay, especially for homeworks. Homeworks are like, free practice. Yay. Okay. So questions on that? That's option 1. That was option 1. So option 1, again, in review, do a U substitution, right, because that's what we need in order to integrate this. Don't the limits of integration here, though, because there are limits of integration for the variable x, we have to, kind of leave them out. We integrate, as you normally would, the indefinite integral, retranslate in terms of x, and then evaluate from 1 to 5, those x limits of integration. Okay? Option 2. Try and squeeze it in over here. Okay? Option 2, we'll still do that same U substitution. Okay? But again, remember that the problem, right, with this integral, the problem why we didn't use 1 and 5 here is because those were the limits of integration for x. If we wanted to put limits of integration in here, we would need to find the limits of integration for what variable? U. How are u and x related? U is 10x minus 1, right? That is how we defined u to be. U is 10x minus 1. So if we want to take this 5, which is an x limit of integration, what can we do with this 5 in here? What should we do? Multiply it by the 10 and then subtract 1. So 10 times 5, 50 minus 1, 49. So our new upper limit for u is 49. Okay. What will our new lower limit for u be? 9. And so when we integrate u to the negative 1/2, it'll be the same thing we had before. So it becomes u to the 1/2 over 1/2. Okay. At this point, I'm not going to write the plus c because we're going to be evaluating this definite integral, this new definite integral here from 9 to 49. Okay. So this is 1/5 times, and if I plug, so I went ahead and just, instead of dividing by 1/2, I multiplied by 2, made that 1/5, and so we just have u to the 1/2. So 1/5 49 to the 1/2 minus 1/5 9 to the 1/2. Okay. And now you can see that we're going to end up with the same thing, right? That was exactly the same calculations we did here. 49 to the 1/2 is 7, 7/5 minus 3/5 equals 4/5. Notice in this case, right, we did not need to retranslate back in terms of x. There was not necessary because we were already in terms of u there. There was no need to go back to x's. Okay, we retranslated everything to be in terms of u since it's just a definite integral. We can if you really want to try and like put your eggs all in one basket, so to speak, I would suggest that you focus on the second one. All right, because it is kind of, I guess, like it shows up sometimes in like multiple choice too. Like, for example, a common AP question that I remember seeing dealing with this in multiple choice is that you'll be given an integral like this, and the AP test will ask you, like, which of the following integrals is equivalent to this one? And what the like answers are, they're all like different like U substitutions, and you want to pick obviously the correct U substitution. And they have, of course, then adjusted their limits of integration to match, what would be appropriate in terms of U as opposed to in terms of X. And so this is just, kind of a more popular way to go there. You might like it too because it's maybe like a little bit less work. Depending, I mean, yes, there's more work here. You have to figure out what the new limits are, but it's up to you. Okay, what you want to do there. Either one is fine. So again, either you forget the limits of integration, okay, when you're doing the U, and you just indefinite integral there, do an indefinite integral, then retranslate back in terms of X, and then use the original 1 and 5, or you translate your limits of integration for X into U limits of integration, and then go from there. Okay, I'll try and like mix it up some here. There'll be some problems where it's like really just you want to do that, but I don't know. Maybe I'll just adjust every time. I might just do that. We'll see. We'll see what I do here. Okay, haven't decided. So anyway, that's letter A. 2 options, right? All right, letter B. Let's take a look at this one here then. So we've got the integral from 1 to 3 of e to the 6 over y over y squared dy. Okay? So, what should we let u equal here? Okay, yeah, 6 over y. Okay, that 6 over y writes inside the exponent of e. So let's, let u equal 6 over y, which is the same thing, if I may, 6 times y to the negative 1. Okay. Maybe that would help too. Okay. And so du, okay, 6y to the negative 1, the derivative of that would be negative 6y to the negative 2, and I'm going to put dy there, right? Don't put a dx, right? That doesn't make sense in this case. We are differentiating both sides with respect to y, since y is our kind of like independent variable here in this case. Okay? And so, which is the same thing as saying du equals negative 6 over y squared dy. Do we have negative 6 over y squared dy in our integrand? No. We just have what over y squared? Yeah, we have like a 1 over y squared, right? We'll have e to the u over, and then, well, over the y squared, so that's like, it's 1 over y squared there. So we need to get this negative 6 over to here, right? So we can do the substitution. Again, we don't have a negative 6 over y squared dy. We just have a 1, really, over y squared dy. Okay? And so we need to get rid of that negative 6, bring it over here for our substitution. So we'll make it negative 1 6 du equals 1 over y squared dy. Okay? And so this equals negative 1 6 times the integral, and I'll worry about the limits of integration in just a second here. I just want to get the substitution in. E to the u du. Right, the du accounts for the 1 over y squared. We still have the e to the u there, so it's e to the u du. Excuse me. So, now we'll plug in our values here, right, to change our limits of integration. So 3 is our y limit of integration. We'll plug that in here. 6 times 3 to the negative 1, which is 6 over 3, will be 2. 6 times 1 to the negative 1, 6 over 1, so it's just 6. A little bit funky here, right? There we have a lower limit of integration that is greater than our upper limit of integration, but that's okay. It's still going to be upper limit, so e, evaluated 2 minus, or the antiderivative evaluated 2 minus the antiderivative evaluated 6, right? So it still is going to happen that way. Okay. What is the integral of e to the u? E to the u. We're going to evaluate that from, again, 6 to 2. Okay. So that equals negative 1 6 e to the, what's the first one going to be? a to the second minus negative 1/6 e to the sixth. Okay. And, we can, like, simplify this a little bit. Minus negative becomes plus positive 1/6 e to the sixth. And so it kind of ends up working out nicely. Anyway, it's probably going to end up being positive. Well, it will end up being positive, right, when you switch it around. Okay. So there it is, 1/6 e to the sixth minus 1/6 e to the second. Okay, and of course, any of these, would be fine answers too. Okay, questions on any of that? Yes.
Can you go over how you got to the part on the very top of negative
Right here?
6? Yeah, like where's the y squared go?
So remember, it's being divided by y squared. So one way, instead of thinking about it this way, right, we think about this as the integral of from 1 to 3 of e to the 6 over y times 1 over y squared. Oh, sorry. Do you agree that that's the same thing, right? E to the 6 over y times 1 over y squared would be this.
Yeah.
So you see it now. There's the 1 over y squared dy right there. There's our du right there.
Okay.
Yes? Yes?
Sure.
All right. Gabe?
So which one did you plug in to get the new limits of integration?
So right. So what are these limits of integration? They are in terms of what variable? Oh, sorry. You're right. What are these limits in terms of then? Y. Okay, sorry, you were right. They are in terms of u. This is the y variables. So what's the relationship that we have that relates u and y? It's what we designated right here. Our choice, our choosing. We said u is 6 times y to the negative 1, or 6 over y. So you take these y's, plug them in for the y's here, and you'll get the relating u's right there from that. Right? Okay, that's all it is. Okay. This is also called change of variables, right? Change of variables. We're changing from, y's to u's and stuff like that. All right. Let's see letter C here. All right. And I want you guys to go ahead and give this one at least not. You don't have to do the whole thing if you don't want, obviously, but at least try and set it up. Okay. This is an application of something we just were quizzed on, right? We want to find f of the square root of pi given f prime, the rate of change of f, is equal to x times the sine of x squared plus pi, and we know that f of 0 is 6. So we know a point on the original function, we know the rate of change of the function, and we want to figure out what f of root pi then must be. So set up an integral that would be able to solve this. So take, like 30 seconds or a minute. Okay? Set up an integral that will allow us to find this. Okay? And it's something that we saw on the quiz most recently too. Okay, questions like this on the quiz. Just, you can set up, yeah, if you want to go ahead and then try it, of course, after you set up the integral, that's great. Feel free to move on. But I'll give you, another 30 seconds here or so to just set up the integral. Just try setting up the integral here. Just try setting up that integral. All right. Simeon, were you able to set up anything here? You think you had an answer for us? At least just for the integral, right? Don't give me the final answer, but what's like the integral here we'd set up?
The integral of x sine parentheses x squared plus pi dx.
Okay. And did you put limits of integration in here?
No.
Okay. So this is one option. So one option is you do the indefinite integral, get that plus c, And then you could find what your square root of pi is at that point too. Did anyone set it up using a definite integral here? So, okay, Leander, how can we set it up?
It's from 0 to pi. Square root of pi.
Okay, the integral from 0 to the square root of pi, and then did you have anything else as part of this?
No.
So this will get us the net change from the 0 to the square root of pi, but only the net change. We want to know what is the value at the square root of pi. Okay, what was the value of the function at 0? So we're going to take the 6, we're going to add to it, which is f of 0 here, right? We're going to take the f of 0, which is 6, we're going to add to it the integral from 0 to the square root of pi. That will then get us our desired, value of f of the square root of pi. Okay? So Simeon's method is a great method too. That will work as well. Okay? But this one will also work too. Okay? So two different ways about going about doing it there. Okay? Yeah, it's kind of up to you how you want to set it up. Okay? I want to set it up this way. But yes, you absolutely could have just integrated this with the plus c then on the outside or at the end there, and then figured out what c was from that, and then plugged in the square root of pi. Okay? Yes, Gabe.
Are we expected to know how to do it like that?
You should be able to do it both ways. Yes, both ways should be able to do it. And again, this showed up on the quiz that we had just a couple of days ago, or whatever. So more than likely you'll see questions like this too on the test as well, right? So you want to be able to do it both ways, kind of thing. Especially because if it was on a calculator section, for example, I could give Simeon something that he can't integrate, by hand. And so he would need to also be able to do this potentially, not just Simeon, but everybody, kind of thing. Because then you would need to use a calculator, right? So it's important that you're able to set this up and understand this method too. So but it's good that we're looking at both ways, two different ways of doing this. So anyway, all right. So now we got that here. All right, Simeon. Well, I'm assuming when did you actually get ahead and do this one?
Yeah.
Okay. So what did you let your u equal in this case? Okay, great choice there. X squared plus pi. Okay, it is inside the sign, and so now we'll just go ahead and take du, which will be just 2x times dx there. Okay, do we have a 2x dx? No, we just have x dx, so we're going to bring that 2 over, make it 1/2 du equals x dx to match what we have. There's the x and the dx. Okay, and so this will equal, I'm going to go down here, 6 plus the integral, okay, of 1/2, ooh, I'm going to squeeze that in here. All right, let me do it this way. The integral from, well, we'll get to the limits of integration here in a second, sine of u du, like that. Okay, so the limits of integration here, I'm going to change them. All right, so we'll plug in the 0 here for the lower limit. 0 squared, 0 plus pi is pi. Okay, square root of pi squared is pi, plus pi is 2 pi. Okay, and we'll just integrate this. So 6 plus 1/2 times integral of sine, negative cosine. Watch those negatives. Okay, watch those negatives, right? Cosine of u, and we're going to evaluate that from pi to 2 pi. So it'll be negative 1/2 cosine of 2 pi minus negative 1/2 cosine of pi. Okay. So you can leave it like that if you want to, right? But of course we can simplify this here, right? Cosine of 2 pi is 1, so it'll be 6 minus 1/2. And then cosine of pi is negative 1, but then times negative 1/2 becomes positive 1/2, and then minus 1/2. Okay, so 5. Okay. So there's that. Alrighty. Questions on any of that?
Can you show the other way?
Other way, yes, absolutely. So if we did it the other way, you would end up with, let's see here, 6 times negative, 6 plus negative 1/2 times cosine of x squared plus pi plus c. Right?
Can you just do it a
I
tiny bit?
don't have this 6 plus.
Oh, right. You don't need the 6 plus because of we're doing, yeah, sorry. You have just this then. Sorry. Just that, right? That's your function. Okay? So we're going to figure out the c value by using f of 0 equals 6. So we'll plug us, 6 in for the y, and we'll plug in 0 for the x. So it'll be cosine 0 squared plus pi plus c. 0 squared is 0, plus pi is pi. Cosine of pi is -1. -1 plus -1/2 is +1/2. We're going to subtract that +1/2 over, and so we'll get, let's see, 11/2 equals c. Yes? Mm-hmm. Okay, and so then we want to find f of the square root of pi, which would then be -1/2 cosine of square root of pi squared plus pi, and then plus an 11/2. So far, so good, right? So again, you could stop here. That is, as far as you need to go. It's, arithmetic at this point, but we could continue. Squaring the square root gives us pi. Pi plus pi is 2 pi. Cosine of 2 pi is 1. Times -1/2 is -1/2. -1/2 plus 11/2 is 10/2, or 5. Okay? So, alternatively, there it is, too. So both work here. Both kind of methods work. All right? Questions on any of that? All right. Why don't you guys go ahead, try and set up letter D. Use option 2. Okay? Try the second option here where you change your limits of integration too. So at least get the setup there. Okay? Identify your U. Okay? If you need to here. Actually, let me do one little thing to help you with this real quick. All right? This limit, right? Since this integrand here, since we have a sum, we can break it up over the sum, and I'd recommend that we do, in fact, do that here. And yes, it's important that you have dt's for both of the integrands there. Okay. So again, our previous, kind of integral tools and tricks and tips kind of help here, right? With the sum, you can break that sum up, okay, and make it 6t dt, and then secant pi t, tangent pi t dt there. So go ahead, and of course then, for this first one, do we need to use a U substitution here? No. For the second one, do we need to use a U substitution? Yeah, you will need to use one there. Okay, so again, so go ahead and just this second one, evaluate that second one. So go ahead and just evaluate that second one there. Or not evaluate it, but come up with the U substitution and then, rewrite it. Okay? I would do the same. So just do your U substitution there. And change your limits of integration, please. Make sure you change your limits of integration for appropriate U limits of integration. Okay. Should have got something that looks like this. Okay. So your limits of integration, your new ones, should be from pi over 6 to pi over 3 because we're going to let U be pi times t, right? The pi t inside the secant and tangent there. Okay, derivative of pi t is pi dt. And then we don't have a pi dt, right? We just have dt. So we're going to divide the pi over and make it 1 over pi du equals dt. And so we end up with 1 over pi integral pi over 6 to pi over 3 secant u tangent u du. All right, so questions on that alone? Any questions on just that right there? That substitution? Yep, please.
Why did you divide by u again? when you're finding du?
Divide by the pi, you mean?
Yeah, pi.
Because when you look here, we're looking to substitute, right? If we're going to change this to be in terms of u, we need our dt to be rewritten in terms of du instead, right? We need to translate all in terms of u. So the problem is, though, to do this substitution, in order to substitute into du, I need to have a pi dt in my integrand. I do not have a pi dt in my integrand. The pi t's, those can be taken up by the u. There's no pi coefficient here with the dt to then do a substitution, so we have to move that pi over to make it just 1 over pi du equals dt to substitute it in. Does that make sense?
Yeah.
Okay. Morgan?
So it doesn't matter, like, if we have, like, the secant or, like, the tangent when we're finding our u? Because I thought I, like, couldn't pick pi over t.
I mean, you can. Okay, I mean, you can pick pi over t, and in fact, this is what we want to pick here. If you try and pick u to be like secant of pi over t, or if you try and pick it to be tangent of pi over t, the issue will be that you're not going to have either of those derivatives. The du's are not going to show up. Like secant pi over t, its derivative will be secant pi over t, tangent pi over t times pi. You'll have a tangent of pi over t, but you don't have another secant pi over t. And same thing for tangent, if you try and pick that one here. So yeah, it's just the pi over t. So yes, you can just pick the pi over t here. Because we can integrate secant u tangent u, right? The integral of secant u tangent u is just going to be secant. So that's why we can do that there. Okay. Now, this gets a little bit tricky when we're kind of working with like two integrals simultaneously here. All right? This one, okay, we just rewrote. This one we're ready to integrate. So since we're two separate integrals, you can go ahead and integrate this thing right now for this next step. Okay? This is more of like kind of like a housekeeping, I guess, rule for you guys when you're like doing, your work or like good math, kind of thing. You can go ahead and integrate this thing and make it, 6t squared over 2 evaluated from 1 6 to 1/3, like that. You can go ahead and do that, okay, just like that. You can say this thing, integrated plus then this thing that hasn't been integrated yet. Okay, so you can do that. That's okay. I know it's a little funky, but I mean, if you want to save on, having to do too much, if you want to, try and do more than one thing at once, kind of thing, that's possible. All right. So we ended with 3 times 1/3 squared minus 3 times 1/6 squared. Okay, again, that's from plus, and now we'll go ahead and integrate this thing. Integral of secant u tangent u is secant of u, so 1 over pi, secant of u, and now this one will evaluate from pi over 6 to pi over 3. Okay, so we'll simplify this sum. 1/3 squared is 1/9 times 3 will be 1/3. 1/6 squared is 1/36. 3 1/36 is 1/12. Oops, I'm off the screen. Sorry about that. There you go. Okay, and then 1 over pi times the secant of pi over 3 minus 1 over pi times the secant of pi over 6. Remember, to evaluate secant, it's like evaluating cosine, right? And then just do the reciprocal of your answer, right? Secant is reciprocal of cosine. So cosine at pi over 3 is 1/2. Reciprocal of that would be 2. So it's going to be 2 over pi there. Okay. Minus, and then secant of pi over 6, well, cosine of pi over 6 is root 3 over 2. So it'll be 2 over root 3. So something like that. Yeah.
Can you run back over how you found your limits?
Right here?
Yeah, real quick.
So again, these were our original limits of integration from 1/6 to 1/3, right? Those were for what variable though? T. Okay. When we rewrite our integrand in terms of u, we need to translate our limits of integration in terms of u as well. So we have this equation that we wrote, right? We said let u equal pi t. So if 1/6 is a t, I'll plug that right in here. 1/6 times pi, pi 6. And then 1/3 times pi, pi 3rds.
And then when you put 1 over pi out in front, like, why is it 1 over pi? Why isn't it just pi?
Because again, how do we do our U substitution? U is pi t. So that's going to take care of secant of u, tangent of u here, right?
Yeah.
Okay. Sorry, I'll show you both. There's the secant u, tangent u. But we need a du as well. We need our du in there as well. You can't just have dt. We need to rewrite it in terms of u. So we don't. In order to do this substitution, right? If I want to substitute right from this point, in order to substitute in for du, in order to plug in a du, I need a pi dt, right? Du is pi times dt. I don't have a pi dt here. This pi t, that's inside the secant, inside the tangent. It's not outside. So we have to divide the pi over to make it 1 over pi du equals just dt by itself, because that's all I've got left. It's just a dt here I got to deal with. So 1 over pi du is that dt. Substitute, replaces. Okay. Yes?
Yeah.
I mean, it's not easy. It's not easy. It's not easy. Okay. And I mean, I guess we can simplify a little bit more here. You know, I don't know if you really want to here. We could say, you know, this is what, 4/12 minus 1/12. So we could say 3/12 plus 2 over pi minus 2 over pi square root of 3. And again, we could get maybe more of a common denominator there, but I don't know. I think at some point, you know, it's just kind of like, okay, or 1/4 I could have said there too, you know, so on and so forth. You get the idea there, okay? All right, let's continue. All right. Now, example 4 here, we're going back to more U substitution, no limits of integration here. We're going to an indefinite integral, so we're going to have that plus c at the end. Sometimes when basic U substitution doesn't work, you have to get a little creative and do some rewriting, okay? My calculus teacher back in high school, he called this tricky U substitution. Okay, tricky U substitution, all right? And you'll see why, okay? So, looking at this problem, right, what is our instinct to let u be? You let u equal. Let u equal 2x minus 1, right? Exactly right. Okay, so we'll let u equal 2x minus 1. So du, right, will be then 2 dx. What's the problem? So we don't have a 2 dx. We can deal with that though, right? I can divide the 2 over, make it 1/2 du equals dx. Right? So I can substitute in for the dx here. I have 1/2 du. But what's the problem? We have this x in front here, bless you, that we can't necessarily deal with, right? Because we let u equal 2x minus 1. But now we still have this x that's accounted for, right? So, and again, you don't need to write this necessarily, but this is what we kind of have right now. We have 1/2 integral of x times the square root of u du, right? And this little x right here is a problem because it's like, well, we can't integrate something if it's not all the same variable, all right? But what do we know, what relationship do we have here between u and x? What's the relationship that we have here between u and x? U is 2x minus 1. So, if u is 2x minus 1, well, doesn't that mean that u plus 1 equals 2x? Right, we add 1 to both sides here, right? If we're saying this is true, then this must be true. And if that's true, then if we divide by 2 on both sides or multiply by 1/2 on both sides, wouldn't 1/2 u plus 1/2 equal x? Right? Yes? So, our x can be replaced by 1/2 u plus 1/2 times, I'm going to make that u to the 1/2. Okay. So that's the tricky part, right? This is like an additional kind of like thing we have to do, and it's just kind of like a clever, not me being clever, just just like we have to be kind of clever with the mathematics here. It's like not a direct U substitution. We have to kind of like also kind of manipulate our little equation here around to then get that x as well. Now, are we ready to integrate this as it's currently written? No. What should we still do with our integrand before we integrate here? Yeah, distribute here that u to the 1/2 through. And so we'll have 1/2 integral 1/2 u to the 3/2 plus 1/2 u to the 1/2. So again, we distribute the u to the 1/2 there. Okay. And now we can integrate. Okay. So maybe I'll go ahead and distribute that 1/2 there too. So let me make this, instead of 1/2, I'll say that's going to be 1/4 here, and make this 1/4 here too. I just don't like having to deal with so many coefficients sometimes. It's too much.
Are you distributing just the 1/2 or the u 1/2?
So I distributed the u to the 1/2 initially, right? U to the 1/2 times each, but then I also went ahead and distributed the 1/2 as well to both.
Okay.
Yeah. Okay. All right. So we integrate here, right? So we'll have 1/4 times, add 1 here, so it's u to the 5/2 over 5/2 plus 1/4 u to the 3/2 over 3/2 plus c. Don't forget that plus c at the end there. Okay, and then we can, instead of dividing by 5/2, we can multiply by 2/5, so it becomes 2 over 20. And then instead of u, we'll put the 2x minus 1 in. And then instead of dividing by 3/2, we'll multiply by 2/3, so 2 over 12. Okay. And of course, if you want to simplify your fractions there, you can do that, make it 1/10. Okay, plus c. But of course, this one's also fine too. Okay. So that is a tricky U substitution. Tricky, tricky, tricky. Okay. You tend, so how can you kind of know that you need to use a tricky U substitution? Well, first of all, one way you kind of know it is kind of like running into the situation that we had right here. Okay, that's kind of one way to kind of indicate, okay, well, maybe something's up here. Maybe I need to try and manipulate around my u equals 2x minus 1. Another way you can kind of tell as well is if the degree of your u is equal to or smaller than the kind of like the thing on the outside here too. Okay, I think that's another way you can kind of like see it as well. Okay, especially if like this is like a degree of 1 and this is like x squared or x cubed or something like that. If what you choose your u to be is is going to have like a degree of 1, and the other thing on the outside doesn't have that, then that could be something as well. Okay, but again, also with just practice, you'll see it show up as well. So let's move on here to example 5, okay? So example 5, we're going to use this graph again. So again, looking at graphs, okay, of g in this case. We want to integrate, or we want to find f, which is the integral from 1 to t of g of 2x dx. We want to find f of 3, okay? So to integrate this thing here, we want to find f of 3. So that would be then the integral from 1 to 3 of g of 2x dx. Okay. Notice here, right, that we do not have the graph of g of 2x. We just have the graph of just plain old g here. Just g of x. This is just g of x right here, not g of 2x. Okay? Does anyone remember what the transformation, the 2x, the 2 inside of g like this, what that does? Yeah, it's going to shrink it. It's going to shrink it by a factor of 2, and shrink it in which direction? It's going to be a horizontal shrink there, okay, of 2. So it's going to like shrink it down by a factor of 2. That's not necessary to do here because we can use what? U substitution. Okay, so let u What's u going to be? 2x. Okay? So then du will be 2 dx. Do we have a 2 dx in our integrand? No, just a dx. So we're going to make it 1/2 du equals dx. Okay? And so then we'll have 1/2 integral of g of u du. Okay. What are our new limits of integration going to be? Well, we're going to plug 1 in for the x here. So 2 times 1, 2. Okay. And plug 3 in for the x here. 3 times 2, 6. Okay. And now we can evaluate this because we've got our graph here, right? 1/2 and then times. So the area under the curve here, right, is what we want. So let's see here. We want to go from 2 to 6. Okay? So you guys go ahead and come up with that, right? I think I've done enough for you there. Go ahead, come up with that. Right? Come up with that value there. The integral from 2 to 6 of g. Okay? Integral from 2 to 6 of g. So find what f of 3 is equal to. Remember that when your graph goes under the x-axis, we should count that region as being what? Negative. So be careful there. When you put that region under the x-axis, you should count that region as being negative. Okay. So we have some parts of our graph above the x-axis, some parts of our graph below the x-axis. So the area is not as obvious as you guess. Oh, I see what you're saying. So, okay. So, if you're integrating g, that means we're using the area of the curve. So it's the area is from
Every time we come up with the long side stuff, and then these are the two big ones.
integral is going to be correct.
That would just get you like a square. And that just gives you a square.
Because the way you're doing what you just did there is you said like, the integral of g is g, and then you would plug in the 2 and the 6. But we have g, we're integrating g, so it's an area. Okay.
How are we allowed to use this graph?
How much you got?
I got one.
I got 2.
I got one.
Yes, but when you have
I'll grab by one
g
and a half
of
again.
u, then just also like g of x would be equal to g.
I got two,
Very much like
with and then multiply it by one.
Yeah, I got 6 for the top one and then -1.
And negative one, and I got 3.
How did you get -1 for this?
No, negative one, so try to
So
3.
this is the graph of g of x. We're trying to evaluate g of 2x, right? Which is different than g of x. Okay, so far so good, right? So by using this U substitution, we now have g of u du, okay, u is equal to 2x. So looking at this now, we can use this because it's g g of our variable here. I think this is, I can see why, I can see what your confusion is, so the x is like views and stuff like that.
You have like 4 of the integrated.
It's like akin to this. Let me say this. If you know that g of x, and let's just make up something here, is this, then you know likewise that g of t is this. Okay? Or g of u would then be this. And that's what we're doing in this case, for this particular scenario. Okay? We have kind of like, in a certain sense, we're given this as the graph, and then we have this for u.
So then should we be able to integrate,
The g of the 2x?
yeah, with the 3
So yes, you can do that here. But you're gonna end up doing some of the questions done right here already. Where you have to just using g, kind of like translate the idea, or like transform the function, because this is a transformation of this function. So we're like untransforming it equivalently in terms of just this, but then that adjusts those limits of integration. Does that make sense, maybe? Sort of, kind of. So yeah. That's kind of the basic idea. Okay. We should have 2 as our answer. 2. Okay. Questions on any of that? Sure. Okay. So are we okay with this? Is the fact that this is 1/2 integral 2 to 6 of g of u du? We're okay with that? Okay. So we look right here. All right. And I broke this up, kind of mentally here. All right. I saw a nice square, 2 by 2. So this is 4. Okay. This triangle right here, okay, is 2 by 1, but half of that is 1. Right? 2 times 1 is 1. Sorry, 2 times 2. 2 times 1 is 2. Half of that for the area is 1. And then this right here, it's a 1 by 2, so it'll be -1. So the 1 and the -1 cancel out, and you're left with just 4. And of course, half of this value, so half of 4.
Is
2.
solving it with the trapezoid wrong?
No, you can use trapezoid here. So you could say, it'd be 1/2. It'd be 1/2. Height is 2. Base 1 is 2. Base 2 is 3. Okay, so 2 plus 3, 5 times 2, 10. Half of that is 5. But then this right here is a triangle, right, with an area of -1. So 5, then minus the 1 gets you back to the 4 still. Okay?
I know that the height, like I remember that like when we did this before, the height was always like the bottom part.
Okay. The height is the bottom part in the cases where we're doing the trapezoidal rule, because those trapezoids are like this. Okay?
So that's not always.
Right. So how do we know which one's the height, which one's the base? The bases are always the parallel sides. So parallel, parallel, right? And then the height is the perpendicular to the base. Okay? So yes, no, it is easy to get disoriented there. All right. Let's press on here. All right, we still have a few more to get through, and then gosh, I do want to get to that back one here, but we'll see. Okay, we don't need it. Okay. So anyway, for letter A, all right, we can do something very similar here to this. Again, the g of x plus 2, we can say let u equal x plus 2. So du in this case is just dx. That's very nice. Okay, it's 1 dx there, right? And so this is the integral of g of u du. Okay, so we can change our limits of integration here. 2 plus 2 gives us 4. 4 plus 2 gives us 6. And so we're integrating from 4 to 6 g of u du. Okay? So from 4 to 6, what will that integral be? 0, right? Yeah, the positive triangle cancels the negative triangle there, and so it gives us 0 by symmetry there. Okay? We're integrating from 4 to 6. Yeah, sorry, I'm sorry. Yes. I understand. It is kind of confusing the fact that we're using the g is the graph here.
It's in bold too.
Okay.
Yeah.
Oh, it is, yes. I also missed that part as well. I just was like, it's got to be this, right? Because what else are we going to do? So anyway, okay. This next one, do we need a U substitution here? Mr. Wood, if you're asking that question, that means the answer is no, right? Because why would I ever ask it otherwise? That's my mistake, I guess. But yeah, we don't need limits of integration here because, or sorry, we don't need to change to U substitution. I mean, we do need limits of integration. We're just going to break it up. There's a plus sign right there, yeah. Okay, so g of x dx plus 2 to 4 of 2 dx, right? This is a sum. Okay, a U substitution here is not necessary. We can just break up that sum. We know the integral from 2 to 4 of g of x. What is the integral from 2 to 4 of g of x? 4. Right, it's just the area. And the integral from 2 to 4 of 2, well, we have to integrate 2. 2 integrated is 2x, if either from 2 to 4. So we get 4 plus, 8 minus 4. So 8 is our answer there. Pretty simple, right? Questions on any of that? All right, we're going to keep going here then. See how far we can get. Hopefully I can finish up through here. All right, number 7. Last example, but it's like a free response style question. All right, so a particle is moving along the x-axis for all t greater than or equal to 0. Okay, so key thing here, we're moving along the x-axis for all time greater than or equal to 0 and has an acceleration modeled by the function that. The particle has an initial velocity, v of 0 equals negative 3, and starts at the origin. Okay, find the velocity function. Well,
It's popcorn.
I was
It's
gonna say,
Brazilian.
it's pretty greasy looking. Sounds delicious. All right, anyway, so given the acceleration, how do we find the velocity? What do we do? Integrate. All right, so we're going to integrate. 8 times 2t minus 1 cubed dt. Okay, and again, we're trying to find the velocity function, so we're just going to integrate indefinitely. We're going to indefinite integration here. Indefinite integration. All right. I'm going to pull this 8 coefficient in front of my integral sign. Okay. Can we integrate this as it's currently written? No. What options do we have here to integrate this? Option 1. Multiply it out. Okay? And that's not too bad, right? 2t minus 1, 2t minus 1, 2t minus 1, 3 times. That's not awful, right? Could be a lot worse, right? Or option 2, we could use what? U substitution. Which one do you want to do? Multiply it out or use U substitution? I heard U substitution. Let's use U substitution. Simeon's going to sit there. He's going to give us the answer for multiplying it out, Simeon. So you just go ahead. Get to multiplying there, Simeon. Just, yeah, I know. I'm sure you'll do it fine, too. But you don't have to do it, really. All right? It's too much. Some of you are probably thinking, Mr. Witt, this whole class is too much. Well, I agree. It can be. It can be a bit much at times. All right, so 1/2 times a is going to give us 4 integral u cubed du. Okay, so again, I went ahead and did the 1/2 du, but there was the 8 there already, so I just went ahead and made it 4.
I know.
Okay, integral of u cubed is u to the 4th over 4 plus c. The 4's cancel, and so we're going to end up with 2t minus 1 to the 4th plus c. And that is our velocity function. Okay? But of course, yes, Lily?
Would we have to find C because we have V of 0?
Right, exactly. So of course, right, we have our initial velocity here. And so we're not quite done yet, right? Because we want to find the actual velocity function for any time t greater than or equals 0. So we're going to use our initial velocity. So 2 times 0 minus 1 to the 4th plus c. Okay, so this is a preemptive circle here. I should have watched myself. Okay, so 2 times 0 is 0, minus 1 is negative 1. Negative 1 to the 4th is 1. Subtract that over. Negative 4 is c. And so maybe I'll do it right here. V of t is really equal to then 2t minus 1 to the 4th minus 4. And that is really our velocity at any time t. Okay, just like that. Okay. Okay, so there's that. All right, next, letter B, we're asked to find the position function. So, given the velocity, how do we find position? Integrate. Okay, so we're going to say x of t. Notice that they're using x of t to describe the position function here because our particle is moving along the x-axis. That's kind of the typical reason when you use the x of t. Okay, sometimes we also use s of t for position, right? But in this case, x of t is the more traditional way to describe it because it's our particle is moving along the x-axis here. So anyway, all right. Okay, now at this -4, we should really break this integral up. Okay, like so, right? The -4 we can integrate by itself. The 2t minus 4, or sorry, 2t minus 1 to the 4th, that we're going to have to use the U substitution. So we'll let u equal 2t minus 1, so du equals 2 dt, so 1/2 du equals dt. Again. Okay, and so we end up with 1/2 the integral of u to the 4th du minus, and I'm going to go ahead and integrate the 4, minus 4t plus c. Okay, because I already have that, because I integrated the 4 there, you got to put the plus c in right here already, okay? So make sure you put that plus c in there, okay? And that's from like that. Integral of something to the 4th is that something to the 5th over 5 minus 4t plus c. I don't need to bring in another plus c, okay? So, yes, we integrated u to the 4th, becomes u to the 5th over 5. We could put a plus c here, but we can just, kind of consider it to be absorbed in with this plus c right here, and that's okay. Okay, so you can just have the 1 plus c. You don't need to write 2 of them, even though we integrated, 2 different things here. We just combine those c's together, and that's okay. So we end up with 1/10, 2t minus 1 to the 5th, minus 4t plus c, and of course, what do we know about our position? It's at the origin, which means the position is 0 at time 0, right? It starts at the origin, so 0 equals 1/10 times 2 times 0 minus 1 to the 5th, minus 4 times 0 plus c. And so we get -1 to the 5th, which is -1. -1 times 1/10, -1/10, minus 0 plus c. So c is positive 1/10. When you solve it out there. Okay, and so our position is 1/10, 2t minus 1 to the 5th, minus 4t plus 1/10. Okay, just like that. Okay. All right, and then we're out of time. So we'll stop there. We'll finish these up. Okay, I apologize. All right, we'll get back to those tomorrow and finish them up. Okay. Your homework will be posted to Google Classroom.